Good morning, students. Sorry for the inconvenience caused. So today we will start with Module 3. Module 3 is about input-output organization. Okay. So Module 3 is from the Chapter 4 of the textbook. Chapter 4 up to 4.2.4 and 4.4 except 4.4.1. Okay. So the topics included for Module 3 are from the Chapter 4 from the textbook Computer Organization by Carl Hamacher. That is the same textbook we are referring throughout this subject. So up to 4.2.4 and then one more topic 4.4 is included. In between 4.4.1 is excluded. Okay. So I want to also tell you that the correction is over and the internal marks are uploaded in the canvas. Okay, if you have any queries regarding your marks, if you want to know the split up or any queries, you can contact me. You can directly call me. So before contacting me, you can cross verify your answer script with the answer key which is shared. Okay. So if you find any problems or anything you are expecting more marks, is some issues like that. Okay. If you have any confusion, you can contact me. Okay. So first topic under module 3 is accessing IO devices. So this particular topic we are not studying newly here. This topic is already introduced in the second module, right? So here we talk about accessing IO devices. Okay. So here the figure is for a single bus structure where you can see processor and the memory are connected to the IO devices. Input output devices, n number of devices can be connected depending upon the processor, how many IO devices it can support. Okay. So why a bus is required? Bus is nothing but a connecting wires, right? Bus is nothing but connecting wire. You have it is not a single wire, right? Bus means a collection of wires or collection of lines, right? What are the different buses we find in the computer system? So those are address bus, data bus and control bus, right? So address signals, data signals, control signals, right? So bus is responsible for transfer of address, data and the control signals. So if the data transfer has to take place between the processor and the IO devices. In the previous chapters, we have studied about load and store operations, right? Data transfer between uh, memory and the processor, right? If the processor is reading from the memory, it is called as read operation, memory read. If the processor is writing into memory, it is nothing but the memory write operation. So what do you mean by read and write? It is the data transfer from the memory to the processor is read operation and data transfer from processor to the memory is a write operation. So processor not only reads or writes into the memory, processor also reads and writes into IO devices, input output devices, right? So Before reading or writing into the input output devices, as in case of memory, first the processor has to provide the address of the input output device from which it wants to read the data or into which it wants to write the data. Very similar concept, okay, similar to the memory. Every memory location will have unique address, right? If the processor wants to write anything into the particular location, it has to first provide its address into the address bus, and data from the corresponding location is placed onto the data bus, right? So similarly here, each IO device is assigned a unique set of addresses. When the processor places a particular address on the address lines, the device that recognizes this address responds to the commands issued on the control lines, right? There may be n number of devices connected to the processor. Each device will have its own address by which the processor recognizes it, okay? If the processor wants to communicate with the particular IO device, its address will be placed on the address bus. Okay. So out of n number of IO devices, the respective IO device recognizes its address and then it places the data onto data bus. Okay. And from the data bus, processor receives it. That is IO read. Okay. So processor can only read from the input device. So then, if the processor wants to write something into the IO device, that means a particularly output device, processor can write into the output device, processor can read from the input device. So in common we call it as input output devices, IO devices. So if the processor wants to write the data, that means if the processor wants to send the data to the output device, first its address is placed on the address lines, and then once the output device recognizes the address, some sort of acknowledgement is sent to the processor, and then processor places the data also onto data bus, and from the data bus output device will receive it. So it is a write operation, processor to output device. So now you have understood the use of address bus and the data bus, right? Now what is the use of control bus? Now control bus is responsible for transfer of control signals. What are the control signals in this particular case? So we have two operations, IO read and IO write. That is, transferring the data from the input device to processor is a read operation, IO read. Transferring the data from the processor to the output device is write operation, IO write. Right. So this read and write signals are nothing but the timing signals which are sent through the control lines. Okay. So that is the use of a control bus. So this is how the data transfer between the processor and the input output device, IO device, will take place. Very similar concept as that of the data transfer between processor and the memory. Okay. When IO devices and the memory share same address space, the arrangement is called as memory mapped IO. Okay. So if the IO device and the memory share the same address space, the arrangement is called as memory mapped IO. In the memory, some portion of the memory is used as a memory itself, means some portion of the memory locations, some particular range is used as a memory, and remaining memory locations, okay, are used for addressing IO devices. Okay, that kind of arrangement is called as memory mapped IO. Memory mapped IO. Okay, so memory will have the addresses which are exclusively used as a memory for the computer system, and remaining addresses or address space is used for addressing the input output devices connected to the computer system. So such an arrangement is called as memory mapped IO, and you already know how to read and write, okay, using memory mapped IO system, right? So for example, with memory mapped IO, any machine instruction that can access memory can be used to transfer data from or to the IO device, right? This is also discussed in the second chapter. Any instruction which is used for data transfer can be used for accessing the memory mapped IO, right? So move instruction is used here. So what is data in? Data in is a register in the input device, right? Data in is a register in the input device which will hold the data. For example, if we are entering a character from the keyboard, as soon as the character is pressed, that particular the ASCII code of corresponding character will be available in the data in register of the keyboard, and processor will take it from there, right? So here the operation is to move the content of the register data in from the input device to R0. So this is a IO read operation, right? It reads the data from data in and stores them into processor register R0. So this is the example for reading the input device in memory mapped IO. And for writing, move R0 comma data out. So that means the data from the register R0 is transferred to data out register. Data out register of the display device or the screen, whatever. Data out is a name used in this textbook to indicate it is a register buffer. It is called as buffer register. Okay. All data in, data out are called as buffer registers. So data out is a buffer register used in the output device. It can be either display, printer, or okay, anything. So this is how the data is read and displayed using memory mapped IO. So memory mapped IO is nothing but if the same memory space is used for addressing memory locations and also IO devices. But some of the computer systems or processors have special instruction called as in and out for reading the input output, sorry, not only reading, for data transfer between input output devices. Okay, so in and out, instead of using move instruction, some of the processors support in and out instructions. So when it's in, by the name only you can make out that it is reading from the IO devices, and out indicates you that this is the instruction which is used to send the data to the output device. That means for the write operation. In is for the read operation, out is for the write operation. Always remember, in means from the input output devices to the processor, data transfer, and out means from the processor to the input output devices. Okay. Now, IO interface for an input device. Usually, input or output devices. Okay, here in this example, input device is considered in the figure. Usually, between any input and output devices, there will be something called as IO, input output interface, or IO interface circuit. So here three buses are shown here. Okay, address lines, data lines, and the control lines. These are the part of the processor. So you have a processor here. Okay, instead of showing the block of the processor, just the buses are shown here. That is only for the ease of understanding, to show you that where these different devices in the IO interface are connected. Okay, inside the processor, they are connected to different buses inside the processor. So here you have a processor, and then you have input device, it can be output device also. In between you will have IO interface. So remember, there will be interface circuit, IO interface circuit. You cannot connect any IO device directly to the processor. There should be an interface circuit to connect any input or output device to the processor. So what are the different components of this IO interface circuit? So you have address decoder, control circuit and data and status registers. So just see where they are connected. So input output device will be directly connected to control circuit and data and status registers in the IO interface. And IO interface also will have a address decoder, and address decoder will be connected to the address lines of the processor. Control circuit is connected to the control lines in the processor. Data and status register is connected to the data lines in the register. Okay. Now why address decoder is used? Address decoder is used to decode the address provided by the processor onto address lines and make it available to the IO device so that the IO device can understand it. Okay. So address decoder will decode the address which is placed in the address bus by the processor, and it will make it understand by the IO device. Okay, so that the IO device can recognize it and then identify itself and then place the data as requested by the processor, or write the data into it as provided by the processor onto data bus. Okay. Then there is a control circuit which will indicate the IO device whether it is a read operation or write operation. If you have a read signal in the control line, that means the data transfer from the input or output device connected here to the processor, and if it is a write signal present in the control line, the data transfer from the processor to the input output device. Now from the processor means where will be the data? Data will be available in the data line. Processor will place the data onto data bus, which can, okay, if it is has to be written onto the IO device. And if it is a read operation, the IO device will place the requested data on the data lines and from which the processor will take it. Okay. Then you have data and the status registers. So you know data in, data out, they are nothing but the data registers. S in, S out, they are the status registers. And you know what are the uses of it. So instead of having this data in, S in, data out, S out registers in the input and output devices, these will be present in the IO interface. Okay. So when there are many IO devices connected to it, there will be interface circuit, and the data buffer registers, data in, data out, which are the registers present in the input and output devices, and the status registers S in and S out, they will be present in the interface circuit instead of being present in the input output devices. Okay. So this is the IO interface circuit, which is responsible for communication between the processor and the IO device. So the circuit will provide the interface between the computer system and the external world. So same thing is mentioned in the form of points, okay, which you can utilize as a notes. Okay, I have explained all these points with the help of the figure itself. So I'll not read this once again. Now consider one example. To review the basic concepts, let us consider a simple example of I/O operations involving a keyboard and a display device in a computer system. Okay. A simple example of I/O operations involving a keyboard and a display device in a computer system. The four registers shown in the figure are used in the data transfer operations. The four registers shown in the figure are used in the data transfer operations. So these are data in, data out, status and the control. Data in, data out, status and the control registers. Okay. So Here you already know the use of data in and data out. Okay, and then in the status register, which is a 8-bit register, you have S in and S out. So you know that S in and S out are status control flag registers, right? So S in flag will be set whenever there is a data available in the data in register, right? As soon as S in flag is set, the data from the data in register is read by the processor. And then as soon as the processor reads the data from the data in register, S in will be reset, right? S out is a flag register present in the output device or the device interface circuit, IO interface circuit, as you have seen in the previous slide. So whenever S out is 1, whenever S out is set, the data from the processor is transferred to the display device or the printer. Okay, so data from the processor is transferred to the output device. It can be printer, screen, anything. So as soon as the data is transferred to the output device, to the data out register of the output device, it will be reset, right? And then we have something called as DIRQ, KIRQ. These are used for the interrupts. These are used for the interrupts. Interrupts is the next concept which we will be studying under this chapter. For time being, we will not discuss about that. Okay. Then in the control register, which is again a 8-bit register, we have DEN and KEN. These are again enable registers or enable flags which are used for interrupts. Okay, so for IO operations not involving interrupts, only data in data out, which are the input and output buffer registers available in the IO devices, and S in and S out, which are the status control flags used, right? So these two DIRQ and KIRQ, DEN and KEN are used for the interrupts. Okay, these are used for the interrupts. But these are the 4 registers which are usually used for accessing IO devices. Okay, so S in and S out are 1-bit registers, right? These are individual bits of a 8-bit status register. Flag means a 1-bit register, right? SN is 1 bit, S out is also 1 bit. These two flag bits are the individual bits of a 8-bit status register. Okay, please understand that. And again in the control register we have 8 bits. So there are some other bits also which are out of the scope of our syllabus and this text. The available or the concepts which are discussing are related to only DEN and KEN. So only those are shown, because in this chapter we are discussing about interrupts and accessing the IO devices. Okay. And you know data in data out is used to hold the 8-bit data, right? So whatever we enter from the keyboard, it will have its corresponding 8-bit ASCII code. So data in is used to hold that, and then when it is sent to the display device by the processor, display device will have a data out register which will take it and then do the necessary action, either printing or displaying. So consider a program that reads one line from the keyboard and stores it in memory buffer and echoes it back to the display. Program that reads one line from the keyboard, stores it in memory buffer and echoes it back to the display. This is a program. So similar program you have studied in the second module also, right? Program that reads one line of characters from the keyboard, stores it in the memory buffer. Okay, it has to be stored somewhere in the memory, and then copy it back to the display. Echoes it back means it is already stored in the memory and copy of it is sent to the display for displaying. So program should do these operations. So what does it do? Again the repetition. Okay, you have studied this similar program under program control IO, accessing, reading a line of characters and displaying. through the keyboard, right, using a memory controlled IO operation. So what happens here? Move hash line comma R0. So line is the address. For timing, you're transferring some address which is labeled as line to register R0, because later point of time you want to store the characters which are entered to the keyboard starting from the memory location line. So initialize a memory pointer R0. Why are you calling it as memory pointer? That is because R0 now holds this address. A register holding address is always called as pointer. That means R0 is pointing to the address line. Now, test bit hash 0 comma status. So you know that to check whether the data is available in the data in register, that means to check whether the key is struck, you have to monitor the S in flag register. So what is S in flag register? S in flag register is bit 0, right? This is the 0th bit of status register. So as per this example, S in flag register is bit 0 of the status register. So you will be checking bit 0 of status register. That means you are checking S in flag register. So that is what is done here. Test bit hash 0 comma status. That means test S in. You are checking the 0th bit of status register. That is nothing but the S in flag register. Branch if it is equal to 0 to wait k. Okay. So if it is 0, if SIN is 0 or bit 0 of status register is 0, that means no key is struck. There is no data available in the data in register. So again go back to wait k and again check the bit 0 of the status register. So till the SIN becomes 1, it will go on introducing the wait loop. Right? Program is continuously monitoring the SIN register, that is a bit 0 of status register, till it becomes 1. That means introducing the wait state, performing no operation. Now, as soon as the bit 0 of the status register becomes 1 or SIN flag register becomes 1, that is a bit 0 of status register, this particular condition becomes false. The control will not be branched to the label wait k because it is not equal to 0 now, it is 1. In that case, the condition becomes false and the next instruction is executed, that is move data in comma R1. Okay, so when test bit 0 is not equal to 0, that means the data is the key is pressed through the keyboard and the data is available in the data in register. So move that data from the data in register to register R1, that is to read the character. So the character from the data in register of the keyboard is transferred to the processor register R1. Next part of the code is wait d test bit hash 1 comma status. Now one character is read, it has to be displayed using the display device. So to display, the processor has to check whether the SOUT register is equal to 1. If SOUT register is equal to 1, that means the display device is ready to display. Then only send the data or the character from the processor register to the data out register of the processor. Now SOUT flag register is nothing but bit 1 of the status register. Right? See, SOUT register, SOUT flag register is nothing but bit 1 of the status register. So you are checking SOUT. Indirectly, you are checking it by checking bit 1 of the status register, which is nothing but SOUT flag register. Branch if it is equal to 0 to wait d. If it is equal to 0, if SOUT is equal to 0, that means the output device is not ready to display. So again go back to wait d and again check the same bit or SOUT register. Okay, so it will be continuously monitored. SOUT flag register or bit 1 of the status register is continuously monitored Okay, continuously the program will branch to wait t till it is 0. And as soon as it becomes 1, that means branch if it is not equal to 0 to the next instruction, right? If it is equal to 0, go to wait d. If it is not equal to 0, the condition becomes false, right? It will not branch to wait d. It will transfer the data from the register R1, the processor register R1 to data out register of the display, right? So that means when SOut is not equal to 0, that means the display device is ready, the condition becomes false, and the next task is to transfer the data from the processor register to the display device. That is what is being done here. Okay. So character is read, character is displayed also. Now there is one more task. It is also told to store it in the memory buffer. So move R1 comma R0 plus. So in the processor register R1 there is a character, right, which is entered and then displayed. R1 has the data. From R1 register it is transferred to some memory location for storing. Which memory location? Which memory location R0 holds? R0 holds the location indicated by the address label line. Okay, and then increment the location. Okay, line plus 1 to the next location. Transfer the character from the register R1 to the memory location present in the R0, that is line, and then increment the memory location. That is what is done here. Then the program has to end as soon as one line of the character is read and displayed. Now, how do you check whether a one line of character is entered and displayed? That is, you have to compare the character entered that is present in R1 with the carriage written. 0D is the hexadecimal ASCII code for a carriage written. When you complete an entire line, the carriage return is entered to start from the next line, to start from the leftmost end of the next line. So that means when the carriage return is entered, okay, it indicates that a line of character is done. A line of character is entered through the keyboard and the program has gone to the, not program, the screen has gone to the next line for the display, right? So it has to continuously check the entered character which will be present in R1 with the ASCII code of the carriage written in the keyboard. If both are same, the program has to end. If they are not same, again read the next character, branch to wait k, then display it. Again store it and check it with the carriage return. If the character entered is same as carriage return, that means the end of the line is reached. If it is not same, then go to wait k, read the next character, display it, store it and compare it with the carriage return to check whether the end of line is reached. So this will go on till the entered character present in R1 becomes equal to carriage return. So did you understand? So what does this instruction do? Compare. Compare means subtract. Subtract destination minus source. So this is source, this is destination. Entered character is in R1, that forms the destination. So destination minus source. Okay, if the result is 0, that means both are same. If both are same means the entered character is the carriage return, the end of line is reached. Then this particular condition becomes false. It will come here and then send ASCII code equivalent to line field. 0A is the ASCII code for line field, okay, to the data out register to display, and then call process. Process is a subroutine, okay, to process the input line. After reading whatever the processing you have to do, that particular subroutine will be called. Okay, you don't have to bother about that. What is the operation performed on the entered line? The program we are interested in is to read a line of character, display it through the key, display it through the screen, and also store it in the buffer. Okay, so when the compare operation output is 0, that means the entered character is same as the carriage return, the result will be 0, right? The subtract operation will give you the answer as 0 if both operands are same. Okay, in that case, it will go to move instruction, right? And if it is not equal to 0, that means the entered character is not same as the carriage return. It can be either more than that or less than this. We are not bothered. We have to just check whether it is same. If they are not same, then the result will be non-zero, right? Result of subtract operation will be non-zero. So if it is non-zero, that means the entered character is not the carriage return. The end of line is not reached. Continue with the next character, right? Continue reading the next character. So if it is not equal to 0, branch if the previous operation result is not equal to 0 to wait k to read the next character, display it again, store it and check it whether the end of line is reached. If it is not reached, again go to wait k, read the next character, display it, store it, then again check it whether the end of the line is reached by comparing with the carriage return. So if it is 0, then this particular condition becomes false. You have to branch only if the result is non-zero. If it is 0, the end of line is reached. Move line feed to the display for the display. This 0 is the ASCII code of the line feed. Okay. So this is the explanation of the same thing. So in the next class we'll start with the interrupts. Okay, we will end here, and in the next class we'll start with the interrupts. So in this particular example, in this program, we have again discussed about program controlled IO, right? We are continuously monitoring yes in and yes out status flags, and depending upon the condition of that, the data is read and displayed by the processor. This is again the similar program you have studied under module 2, very similar to this, right? So that was the example for program controlled IO, reading the input device, writing onto display device by continuously monitoring the status flags yes in and yes out. Okay, so now that example illustrates program controlled IO in which processor repeatedly checks a status flag to achieve the required synchronization between the processor and an input or output device. Okay, so continuously checking the yes in and yes out flags or continuously monitoring yes in and yes out flag registers for reading the input device and displaying onto the output device is also called as polling. Polling. Continuously monitoring something is called as polling. So we say that the processor polls the device. There are two other commonly used mechanisms for implementing IO operations. They are interrupts and direct memory access. Right? The concept which we discussed today under module 3 is nothing but program controlled IO, right? Accessing input output devices using a program controlled IO, which was also discussed in module 2, and we also checked the instructions which can be used for memory controlled IO, right? A simple move instruction is used to read data in and to write into data out, right? So in this chapter, the main stress is given for studying about two new concepts of accessing IO devices. They are interrupts and direct memory access. So interrupts and direct memory access are very important concepts, okay, in the computer system, which are used in all the computers. It is a main principle of operation of a computer, in particularly accessing IO devices, which will be discussed in the next class. So in the next class, we will discuss about interrupts. Okay. So about the internals, the performance in the internals is very poor, which you can make out by looking at your marks. Okay. So it is compulsory for all to write the solutions, okay, in your notebook, and I will ask later to upload it. Okay. So later when the time is given to upload, I will not give more time, because you have to write and keep it ready by next Tuesday. Next week Tuesday is a deadline for you to write it in your notebook. So later when it is asked to upload, you have to immediately upload. For time being, you don't have to upload. Write and keep. So please write question along with the answer. Don't just write the answer. First the question and then the answer. All 6 questions question, answer. Okay. Each question should be followed with its answer. Don't write questions separately and the answer separately. In the form of question answer, you have to write it, all the 6 solutions, and don't simply copy it from the answer key. Okay, answer key is shared where the problems are worked out, and for the theory you can refer the textbook or the PPT. Okay, but you have to write everything neatly, and problems don't simply copy from the text, from the answer key. Problems such as the number system problems and big Indian, little Indian formats, representation and writing the program, all that. Please work out, okay? Refer the answer key and work out by yourself. Don't number by number copy it, okay? So refer, check how it is done in the answer key, and then you by yourself manually work out and write it in your notebook, okay? So thank you. I'll close the class here.